Dear guests, dear colleagues, welcome back after lunch on a third session for today's workshop of Urban Geology and Geotechnics, hosted by ELGIP and Eurogeosurvey's Urban Geology Expert Group. Now we will have 9 presentations in a second batch of the workshop. We start with our supporting partner, SoilCloud company. It's a provider of geotechnical data management solution. Mr. Tomasz Daktera will give us a presentation about the geotechnical database of the 21st century.
Okay, I'll begin. Hello, everyone. Great to have you here in Łódź, Poland. My name is Tomasz Daktera. I am a co-founder of SoilCloud. My presentation is called Geotechnical Database of the 21st Century. I'll try this not to be a presentation of our software, but rather a technology awareness thing. I want geotechnical engineers, geological engineers really to be aware of the technology we have today and that we're not fully using yet. Our experiences are based on the users of our software. Today we have about 2,000 users with over 100,000 projects, which is over, almost 500,000 points, new points with data every year. Our clients are mostly in France, but not only. We have some clients here in Poland. We have some clients in Europe and some other countries. About 70% of all data related to geotechnical engineering and geology for France are imported in SoilCloud, so over 50%. The founders are Lucas Jeannadet and myself, and we are geotechnical engineers, so really civil engineers focused on geotechnical engineering. I believe what we provide for our clients is something different, not just a software, but we also provide our clients with assistance on all kinds of projects and really automation of their everyday tasks. For example, we have assisted Grupa HGS, so EGS, on the CPK, so the largest construction here happening in Poland right now, between Warsaw and Łódź. So on the left, you can see a map of the made ground layer depth. So that was 11 kilometers long, so you can see the depth that goes between 0 and 5 meters for the whole 11 kilometer section. And on the right, you have full statistics for every parameter and every soil layer. So this has been submitted to the client as a full parametric analysis of 1,800 boreholes, I believe. We have assisted another client here in Poland, Bars, somewhere sitting somewhere. With fully automated CPTU imports, analysis of reporting with calibration checks, data quality checks, we're really trying to automate as many tasks as possible for each of the users. SoilCloud. So in SoilCloud, you can have, so you input your geotechnical investigation data, and then you have visualization features, analysis features, and reporting. So everything is really in one software package, so not different software packages, but one software package. You can have your borehole data, you can have your in situ tests from PMT, DMT, CPTs, laboratory test results. We distinguish geotechnical and geological descriptions, so you can have both. There is a full features related to parameters, interpretation, analysis tools, and then statistics, what we've seen previously. SoilCloud is a web software with cloud servers, and what it means for us users. So first thing, it's a tool of the 31st century. It's not written in the 1990s. It's a software of today. So there is no really training needed. Like for those of you who have Facebook, you don't need training for Facebook, right? So you shouldn't be, you shouldn't require training to use a software. But in terms of technical, more technical things, it allows us, for example, for real-time data transfer. Most of our bigger clients in Europe, they switch from manual input to automatic inputs. So for example, on-site tablets, so we also have an on-site, so a tablet interface to input your data. Then they have data logging systems with SIM cards, where the SIM cards directly send the data in real time from site to office. So this is, I think for some of the future, but actually it's a thing of today. Of course, multiple people can work on a same project at the same time from multiple locations. Availability in real time. So for example, you can give access to your client to your project in real time. So he doesn't have the ability to edit the data, but he is able to preview the data in real time. For example, measurement while drilling in real time. So with the data logging systems and the SIM card directly on the machine, this can be sent and seen in real time on SoilCloud's interface. It's a web software, so all kind of updates are instantaneous, which means you can do them. We do them more or less every 2-3 days. There's no installations, no servers. Everything is on our site, so this is not something you deal with. It's like Facebook, as easy as Facebook. For example, a new feature we have added last week, so the log of changes of everything in the project, so you can see who has imported what kind of data and when he has edited and deleted data. So a log of all the changes for a project. The environment and implementation of SoilCloud. So we create an environment that suits exactly your needs. For example, automated reporting. So it can be really configured the way you like it, the way you want it. Visualizing your data by default. So you're not having the same application as everyone else. You have your own where you can save all of this information. You can, so we have a full interface where you can input your data at the office. So we're compatible with Excel too, of course, if needed. But these tables here, as you can see, are different from client to client. You can configure those. Manual, so tablet interface used on site. It works offline too, so offline and online. Reporting, full report creator. Well, you can really combine all kind of data you can possibly imagine, all kind of formulas. We have a Python module embedded in the software, so you can create your own formulas if needed to. An example, if you want to do the interpretation for 20 CPTs, you can probably do it under 10 or maybe under 5 minutes. Why do we need a database? Well, a database, we need it to use data from past projects, to get your data to, statistics, parameters. We want to preview past data. We want to add this past data to active projects. So all of that can be done in SoilCloud. You can add your data to cross sections. You can really use the full database, not just the database from your particular project. A couple of words about the EGS format. Some of you work more and more on the EGS format. So our UK representative is one of the creators of the EGS format, so it shows how serious we are in terms of EGS. We have a separate EGS database in parallel to what we do, so the user has access to let's say two databases at the same time with the EGS format file. But what's important here to say is that the EGS is not a database format. A lot of geotechnical engineers are still not aware that EGS is not a database format. It's a text file with redundant information, which is not a text file. It's important to say it again and again, because we geotechnical engineers are not IT people. We are geotechnical engineers. So this is the EGS module where the user can import, export, visualize, filter EGS data. So you can import multiple files from EGS. So we are fully compatible with 411 and 404 EGS. This tool is used by the UK market a lot. I'll I'll come back to my first slide, technology awareness. Are you a data company, or are you a PDF report selling company? This is an important question we need to ask ourselves. Or maybe, did you try to send an email with your fax machine? I never did that, but, or perhaps with a 33 Nokia mobile phone. Well, no. So why are we still using technologies from the 1990s to manage what's the most important within the companies, which is data? Technology from the 1990s doesn't allow some things, and then doors will be closed and the data will be gone. For example, software from the 90s will not be able to cope with technological transformation, real-time management, API protocols, XML files, 3D modeling will real-time, multiple people work on 3D models, imported photos with geological location, so geolocation, and more. Once again, we're here to optimize the tasks for our client. Well, I'm just there if you'd like to chat. Thank you.
Thank you, Mr. Tomasz, for excellent presentation. We see that the development of modern geotechnical engineering and engineering geology needs modern tools. There are companies that they are pushing the innovation in fields of technology of geological and geotechnical databases. Now we will have an online speaker, Jan Jelenek from Czech Geological Survey.
Hi, hello.
Yes, the next presentation will be focused on CIM, City Information Model. And Jan, we would like you to connect and present online. Thank you.
So hello, I'm glad that I can be present at least virtually. So hi to all. Today I would like to talk about our small project where we try to improve the communication between our survey and our partner city, which is a city of Liberec in the north of the Czech Republic, and where we try to build so-called GeoSim model for them, just a pilot. So as we all know, the cities are facing quite a bit of challenges in this time. So from one side, there is a pressure from the increasing number of inhabitants. The space is limited, and from the other side, we have like the let's say climate change. So geohazards are pushing the cities towards some decisions, and these all are creating some conflicts. And that's why we try to offer to our partner city some solution how to better manage the space underground, the subsurface. So what's the GeoSim? I believe that most of you already know that, but this concept has been introduced by the preceding project of the Urban Geology Expert Group. Many of the colleagues which are in Poland were there. So this is something which includes all information in the city, including beams and let's say when we go more wider to the city quarter city. But with GeoSim we go much into the deep, but we also include information from the above. We can use, for example, like remote sensing data to do some analysis, and included all of it inside of a 3D model which can serve to the city. So this is like the basic image which we are showing to all the city partners to tell them and to show them what actually we can do for them, what kind of information can be included and what can they take from it. So we have a surface, so the cities usually have only the data from the surface and from the very shallow layer below the surface. So they have like models of the buildings, they have some kind of passportization of all the features in the city, like where is the green parts of the city, where are the infrastructures, pipelines, where the water streams or some pipes, etc. But this is usually where it ends for them. So we try to offer them more layers. Actually, anything we possess, and Geological Survey usually, and Czech Geological Survey certainly possesses a lot of data from the subsurface, and these data are usually free because we are public office and we are obliged to provide these data for free, especially to a public entity like a municipality. But as I said, the cities scarcely use these, and they on the other side, they are not obliged to use it, but we try to explain to them that these data might be quite of use to them. So we have a groundwater there. We have some kind of rock permeability. We have undermined areas. Many cities in the Czech Republic are undermined, so this is a big geohazard there. We have a geothermal potential, which can be some kind of analytical layer on the top of the static layers, which we have or which we have right now. And this all is modeled in 3D. So the idea is that the city officer or anybody who is entitled by the city to use this model can basically get the information from the model by clicking on it and like getting the vertical, let's say, virtual borehole with all the conflicts there. It's important to say that each geostatic information model can be customized for each of the cities. So when we communicate with the cities, we always tell them, okay, we will focus on your concrete problem. Here we have Liberec, which is a kind of a boring city from the geological point of view. But we have like the city of Ostrava in the east, which is heavily undermined. And when we come there, we can say, okay, your problem is undermining. You have big collapses here, and it's a huge problem. So we will customize your geosim according to your exact needs, so you can get the most of it. But now to the pilot site. So we have chosen this city in spite of its it is quite boring, as I said. However, we have a big cooperation with the city, and the municipality itself is quite welcoming to us. So that's why we use this city. The city is located in the north, quite close to the Poland and Germany borders. It's below the mountains, so parts of the city already occupies the slopes of the mountains, which can create some kind of conflicts as well. It has approximately 100,000 inhabitants, so it's a moderate city, and as you can see, the topography can go up to 1,000 meters above the sea level, including the inhabited areas. However, what's really interesting about the city is very long history of anthropogenic deposits. We have quite a lot of war shelters. We have a huge amounts of anthropogenic historical like remnants. They change the water streams. They put all like many materials in the valleys to make the city flat. However, before it wasn't flat, there were like deep valleys. So it's quite interesting, and we discovered that the municipality have almost no idea what actually is down there. So what's the geological setting? From the geological point of view, the city is located mainly on crystalline rocks. However, as we can see on the western half of the city area, we have sediments, and these sediments can be quite thick. On the eastern part, we have a pure granite, which is usually severely weathered, up to 25 meters depth. So it's basically sand. So what kind of data we have collected and we have included in the model? We have partnered also with a with the Museum of North Bohemia, And they have large archives of all the plans and all the historical developments of the city. And very unbelievable thing is that this museum has never cooperated with the municipality. It's unbelievable because they possess a lot of data, but these data were never used in the urban planning. So we have put all of these into the model. Then we have used all of our data. Of course, we have a geological maps, we have slope susceptibility map, we have boreholes, we have radon, we have hydrogeological data. Of course, we went also in field. We documented all the outcrops in the pilot square. As you can see, we did not do the whole city. It would be a lot of work. It was not feasible. But for the pilot, we just did the small square like that in the center of the city. So we had there also the historical things, but also the recent things like this this big hole which was created by construction, which was interrupted. So we did UAV models. We used documentation of the geological, hydrogeological features, and all of that was put it inside of the 3D model. So for 3D modeling, we use Move software, and here we can see a basic view of the environment in the software with all of the data. We can see that in our pilot area, we have 3 geological faults. The small dots, these are all the boreholes and all the layers. We can see the groundwater level intersecting the surface, and also the infrastructure, pipelines, etc. The city provided mostly the surface data, like the 3D models of the buildings, and also detailed technical plans of electricity, gas, sewage, and water pipelines. Sorry. So as I said, the most interesting thing is the archival data, and we can see that from the beginning of 20th century, we have a lot of data like old sewage, old like river streams, artificial ones, because they wanted to make the to be the like to have the river at the place they want, not where it's natural. Old mill races from 1902, 1906, war shelters below the castle, old drainage tunnels, etc., etc. So the final GeoSim model, as we present it in the city, can serve as a perfect base for conflicts displaying. Like we can see here exact places where the groundwater level intersects the war shelters. In fact, these shelters are mostly forgotten. They are not like accessible from most of the parts. We have like hobby, let's say, cave speleologists who went through all of it, but the city, they don't have any idea how it looks like. So, and these are the places with potential to become more problem, of course. Here we can intersect and highlight all the buildings which are conflicting with some of the other layers, for example, like 100-year flood or some stability problems or groundwater level, etc. So in order to make this model most accessible, to make it the most easy for the city, for the city officers who usually don't work with any 3D software or GIS or etc. We try to build 2 solutions to make their work with our system the most easy. The first one is open source, because we know that smaller cities in Czech Republic, they don't have any, let's say, GIS. So for them, we built all of it on QGIS, and especially on QGIS 2.3.js plugin, which enables us to create a basic 3D viewer on HTML. Anybody can click on the surface and get such a virtual borehole with the intersection and the depth of intersecting layers. All of these links should be working, so I invite all of you to check it, how it works. Unfortunately, it would be probably in Czech, so sorry about that. The second solution is based on ArcGIS, because again, we know that the bigger cities, they use also almost in monopoly, they use ArcGIS technologies, Esri technologies. So they would probably not want to use some other technology like QGIS. So we try to build also 3D viewer on this technology. So again, this is a different solution. So by that, we try to build portfolio we want to offer or we are offering to other cities in order to get financing for such a model for them. So that's all for me. Thank you for your attention, and I'm open to any question by email or directly. Thank you very much.
Thank you, Jan, for very impressive presentation. We see how the complex solution like GeoSim, hosted by Geological Surveys in collaboration with cities, are essential to build 3D models and then transfer this city or district information into site scale, that planning new infrastructural projects or complex geotechnical works, these tools can significantly decrease geotechnical risk and make our job easier. And if the cycle, then after projects, this data will be imported into such systems, we will have a cycle of iterations giving more and more information about the subsurface and underground features and assets of the cities. Now, we will go for another presentation. It will be a presentation about the feasibility and potential study for the use of geothermal energy in two German railway tunnels by Hauke Zachert from TU Darmstadt from Germany. Please start the presentation.
Thank you, Gregor. Dzień dobry and good afternoon. Welcome to my presentation about the feasibility and potential study for the use of geothermal energy in two German railway tunnels. My name is Hauke Zachert. I'm the head of the Institute of Geotechnics at Technical University of Darmstadt, and this work I'm presenting here is a joint work together with our friends, let's say, from the ELGIP group from Torino, and this is a group of GeoSolving and Marco Bala, who are co-authors here in this presentation. So actually, I plan to give you an outline of geothermal energy and the use and so on, but I can skip the first 10 slides, I would say, because we have seen all the justification of why we need geothermal energy, what type of structures we have, why it is good to replace our household consumption, energy consumption for the heat production by renewable energies. I looked up the values for Poland, and about 30% of the total energy consumption in Poland goes to the private households, and thereof about 60%, 65% go to the heating. So that means about 20% of the total energy consumption in Poland could be replaced by renewable energies with geothermal energy if we can really use the full potential. So that's really something we should look at. And we have seen that instead of building new structures in the ground, heat exchangers, we can actually use the ones we have, these energy geostructures, which were shown by Julia Prodan this morning. And so we are not doing deep geothermal energy like the guys from Berlin here, but we are looking at the shallow geothermal energy. So we can have different type of structures in piles, in diaphragm walls, in parking lots. But here in this presentation, I'm going to focus on tunnels. So tunnels to extract or to use them as a heat exchanger. What are energy tunnels? We also have seen that very briefly. So here you can see how it is typically done. So you insert some heat exchangers into your tunnel lining, and with these heat exchangers, you then extract the energy from the ground. This has been done in real projects already, but these are typically research projects or demonstration projects. So it can be done either directly on the ceiling of the tunnel, where you then pour the concrete after that, or, and this is the most common way, that you introduce it into your precast segmental linings. And this, of course, has some advantages because you use these linings, which you have to produce anyway, and you just have to introduce some pipes actually for your heat exchange. And since these linings are built in factories, that's also very convenient. So you don't have to deal on site with so many additional piping and so on. So that's why it's convenient. So you see here from the literature that some of these things were already done like about 10, 15 years ago. But still, these energy geotunnels are not in use in Germany. So that's why we were appointed by the Deutsche Bahn. It's the German, the German railway operator. We were appointed to make a feasibility study on to explore the energy potential, which is really there if we really activate a full tunnel, and to check whether it's really technically feasible within their specific constraints. And we should do this for 2 projects in different geology, and that's what we did. And you should know that Deutsche Bahn aims to be CO2 neutral by 2040. So that means they really have to invest in all types of fields to make their production and their services CO2 neutral. So this is a map of Germany. This is where Darmstadt is. So this is where I come from. So here we have Frankfurt, so that you see where our university is based. We looked at a project in Hamburg, so in the very north of Germany. This is the route there, which we looked at. And here on the bottom, you can see some data. So it's the Verbindungsbahn-Entlastungstunnel. It has a total length of about 13 kilometers. So that's the 2 rows, and we have a twin tunnel. And the second project is located in Stuttgart, so in the south of Germany. And there we have, of course, a totally different geology, and we have approximately 22 kilometer length here. It's again a twin tunnel. So what was the idea here? It's a feasibility study for Deutsche Bahn, so they will not spend hundreds of thousands of euro to know whether it is feasible or not. So what they wanted is a simplified approach, and that's what we offered them, and that's what we did. Together with the guys from GeoSolving, we actually used the nomogram approach developed by Insana et al. And published in 2020. And this is very nice because here you have such nomograms, and I only brought 2 of them. You have some more in the paper. And these nomograms allow you to extract the geothermal potential in watt per meter square by, here on the y-axis we have the ground temperature, and on the bottom we have the groundwater flow velocity. And if we look here, we can see easily, of course, that if we have, this is, sorry, I need to tell that. So here we have the winter case, so this is heating with the geothermal energy, and this is the summer case where we apply geothermal energy for cooling our buildings. So here, of course, we see that the higher the ground temperature and the larger the groundwater flow, the more energy we can extract from our ground. Of course, these nomograms come with some limitations. We have a full operational load of 30 days. This is what is assumed for these nomograms, and we will come to that later. So now, if we want to apply these nomograms, we have to follow a certain procedure, and that's the main topic you should learn here today, or you should take with you, so that you can see how you could apply this simplified approach. What you do is you need to define tunnel segments or sections with a constant geology, with a constant cross-section, and with a constant groundwater flow. And if you have this, then you can apply these nomograms to extract the geothermal potential, and with that actually then sum it up for your whole tunnel. But because of this tunnel has, or these nomograms have some limitations, obviously, what we did here is then to do some spot-wise finite element simulations to actually verify how close we are with our nomograms to the more realistic design. So now let's have a quick look at the projects. The first project is Hamburg, and here we can see you have different colors here along this line, and these colors stand for different construction methods. It's typically tunnel boring machine, these two tunnels. This is what we see here in red. And then we have some orange or yellow parts, and these are cut and cover. This is typically where we have the stations. So we took all of these and we applied these methods there. One is for the tunnel, and there are also other nomograms which are capable of dealing with diaphragm walls. This is what we did here in these cut and cover sections, where we activated these diaphragm walls. We did not activate in our study here the bottom slab, which would also be feasible. Deutsche Bahn asked me to make sure this is not a fixed route, so this is just one of the route we've chosen here. So it could also be another route which will be built in this tunnel, so this is still in an early process. We had to develop a geological cross-section, of course, along the route, and this is what we see here. You see a lot of silt here with some sand, and here you have typically sand. So you see along the tunnel we have very different geological layers, and of course we also have different geothermal properties. That's something we need to consider. And now what we see now here is how we separated this tunnel now in different segments. Every color is another segment, and this is then reflecting the different construction method and the geology. So, and then we extract from public data the temperature which is along this route, so you get this ground temperature. We can assign this to the individual segments, and of course we also look at the groundwater flow, and this groundwater flow we need the velocity and the direction. And this is also then steering. Of course, it makes a difference whether the groundwater is flowing in parallel to your tunnel or orthogonal to your tunnel. So that's what you need to consider. With all this, we come then to this slide, and this is actually, it looks very unspectacular, so a bit boring maybe, but what you see here on the bottom left is the potential. So you see here a heat map, and for every segment you know now how much energy you could extract in this segment. And now it's rather easy to sum these up and to come up with the total potential you have for your tunnel, and this is what we did in these spreadsheets. Yes, of course you cannot read that. This is due to confidentiality. The Deutsche Bahn didn't want me to show the whole data. So, but this is how it actually looks like. So you have, for every segment, you have all the data, and you can then say, okay, this segment has this energy potential. So that's more or less the process, applying the nomograms to that point. So now we rush through the same thing for Stuttgart, but no need to go into details there because the process is the same. We see here that everything is red, so that means it's all tunnel boring machine, just a few meters of cut and cover here at the beginning and some conventional tunnel method here at the end. So it's 22 kilometers long. But we have a totally different geology. We have here clay stones, some sandstones, and as well marl. So we have a totally different porosity and so on. And we have almost no groundwater. So I'm jumping over this temperature curve here, and we come directly to the groundwater. What you see here is that we have almost no groundwater flow, only here at this part a little bit. So that means we have completely different conditions, and that was also, of course, intentional, because we wanted to have really different conditions for this study. So, and then we arrive at the potential, and here we see that we have quite a good potential here along this tunnel. What you can also see here is, of course, it's not very populated. So that's always a point with this tunnel, or with this geothermal energy from tunnels. You need, of course, also to have your users, your end users, somewhere close by. You don't want to transport your warm energy or your heated energy somewhere. So that means here, these areas, which are mainly covered by the forests, they will probably not be activated. But here are some buildings, and here especially are some schools, which are very, very much interested in the topic. And currently, this project is really going to continue the development and going from this preliminary feasibility study to real application, and really exploring the option to do it, and not just speak about it. And again, we have here a table which then gives us the potential. So I said earlier, this is based on the nomograms. So that means 30 days full power, but we don't know what about 40, 50, 60 days, would it change? And of course, it's also dealing with the assumptions in the nomograms regarding the inlet incoming temperature, outcoming temperature, and so on. So that's why we performed some numerical simulations, or GeoSolving performed these simulations on some spots, and the aim there was to improve the accuracy of our predictions, of course, to validate our assumptions, and especially to check for the interactions between these two tunnels, because the nomograms are assuming a single tunnel, and you can imagine if these two tunnels are too close to each other, then we might get a severe interaction. So I will not bother you with the details of that, just looking in a few results. And what we see here is the heating period, so winter, for Hamburg and Stuttgart. You see in Hamburg the tunnels are much closer to each other, and we can see that for 30 days of full operation, we already have a certain interaction here in the temperature profile, while in Stuttgart we have no interaction of these two tunnels. And for 90 days of full load operation, we see that here we have a very strong interaction, in this case in Hamburg, while we have almost no interaction, still no interaction here in Stuttgart. So this is also one point where you see the advantage of the finite element model. Now you can let it run your simulation for 90 days or operate 100 days, whatever you want. You could also check how sustainable it is over the whole production period of maybe many years, not just one season. Yeah, so that's something where you still need the finite element simulations for. And we also observed another topic, and this is that we have so little extraction of the energy that actually the difference between, or the spread between, the incoming temperature in the geothermal, in our heat exchanger, and the outgoing temperature was too small for the heat pump operators, actually. So that's why we then coupled two of these rings to let the absorbent actually run longer through the tunnel and absorb more energy. So that's something which is also different to the nomograms, and that's why we needed to correct our nomogram results. I can tell you, so in the end we created some correction factors based on these numerical simulations, and these correction factors lay between between, let's say, 5% and up to 27%, which we needed to change the values from the nomograms. And this is mainly due to this interaction of the twin tunnels, but the other part is also this, this fact here that we had to change these temperatures. So, summing up, we come to this final energy potential, and this table is not as bombastic as it or is not as boring as it looks like. So we have here heating and cooling time, and we have Hamburg and Stuttgart, and maybe you just have a look on these values. So if we look for 90 days full operation, we have about 18 megawatt we could develop, or we could extract in Stuttgart, of course, assuming that we activate the whole tunnel. Yeah, so this is the whole 22 kilometers. And in Hamburg, we could finally 3.7 megawatt activate if we have 90 days of full load. In the cooling, we can even we could even do more. It's important to say that typically, or many municipalities are not so interested, at least to my impression, in the cooling. But I always advocate for, please think it with you. One thing is that in future climate change and so on, you will have a need for cooling. You can make your houses more appealing. But especially for the use of the geothermal energy, it's of course very beneficial to actually use your structure also for cooling, because then you are heating your ground in summertime and you can extract that energy again in the wintertime. So it's very beneficial for the use of your geothermal system. And I made a very rough estimate. So this Stuttgart case could be sufficient to supply 5,600 households with renewable energy in terms for the heating. So not, of course, electricity, but for heating. And this is quite something. In the beginning, I said that the title is Feasibility Study and Energy Potential. So I would also like to say at least a few words on the feasibility. In our study, this took a larger component, but there are many things Deutsche Bahn don't want to be shared, so like cross-sections and so on. That's why I take a dummy cross-section here from a blurry cross-section here from literature. Things you need to solve, and you need to start with that very early in such projects, and this is also what you reported from Berlin. It's always you have multi-stakeholders in these things. So it's not just that you say, okay, I operate now this thing and that's it. You need to, in terms of Deutsche Bahn, they need to solve who is actually going to operate the system, because they have different entities. One is owning the infrastructure, the other one is operating the tracks, and the next one is maybe supplying the energy. So who is actually the owner of this system? Who is going to pay for it? And who is actually going then later on to use the energy or to sell the energy? To whom? So these are things you need to discuss and you need to develop. Of course, you need to have a proper idea of the piping. We did a very thorough analysis of the piping with all details, but we stopped at the point where we come to pumps, where we go outside, where we say, okay, this is now how the heat is transferred into the buildings. This then really depends completely on the user of the energy. So this was not part of our study. One very important part is what type of material do you use for these for the distributing pipes, because of course you need to connect these different segments. And the question is, could you place them here in your subgrade or in your concrete? Then you can use PE, that's cheap, that's the standard application, but you can see on this sketch it's already very crowded in these typical banquets. So it might be that you need to go into this area, and then you need to, at least in Deutsche Bahn, you need to use stainless steel because it should not be inflammable. And then that really makes the things a bit more expensive. We came up with some cost estimate. I'm almost done. we came up with a cost estimate of about 1.6 to 2.7 cent per kilowatt hour in the production. As I said, excluding the heat pump itself. Yeah, so that's something which will add on there, but it is for sure quite reasonable and quite cheap. So to sum up, we found that these nomograms developed by Insana et al. Were very, very useful to come up with a good estimate and a proper estimate of the potential. Okay, don't know why this is appearing here, but we have the energy extraction for the German railway tunnels. It is technically feasible. It had really high potential and is very cheap. So as I said, they are seeing a high potential now there as well, and they are going to continue with that. And I really recommend to do some spot-wise finite element simulations to improve the quality of the nomograms. A nomogram cannot really do a final design, of course, of such a big project. I think that's clear. And with that, I thank you for your attention.
Thank you, Hauke, for brilliant presentation. We saw how the innovative technologies can be used to use urban subsurface as an energy source. And this is example that such an feasibility studies are essential to consider that stakeholders will make a decision for full-scale implementation and will allow to move this technology from demonstrators to the full-scale application. And as you mentioned, you use public available data as input. So if you would be able to easier use data from SIM models or other, so there will be like unified exchange of data, you will be able to make more this kind of sizes or more variants. So this will be more efficient and there will be more innovation. So thank you again for your great presentation. And now we go for another presentation. Now we move to Brussels. There will be a presentation by Xavier Devleeschouver from Geological Survey of Belgium, and it will be about geohazards in Brussels, a case study. Javier, please present.
Can you hear me? Yeah. Thank you, Mr. Chairman, for the introduction. We will deal to geohazards in Brussels. So to explain the context of the study, this is what a citizen observed after a good night hole in his garden. The collapse was on the 12th March 2023. And after a few analyses around, the impression was that it is due to a water leakage issue. Almost 1 year later, the request of the owner arrived in my email box. So, and I went on the 7th of March 2024. And I have, of course, very quickly a different explanation about this problem. So we will try to explain this to you in the few next slides. To explain where we are, this is a Google map. You have the center of Brussels here, the King Palace and Park. These are EU building sites. The Geological Survey is there, and the house where the problem is arrived, so the event is located nearby. The geological conditions are the model that my team has produced very recently for the Brussels area. We did the 2D and 3D model, where basically Brussels is subdivided with a low, flat alluvial area on the west and hilly side on the east, where the yellow is the Brussels formation, composed essentially of very thick sandy formations, almost 90 meters. And where are we? We are on top of one of these hills here in very specific geological formation, where the one that we will talk about is the lead formation. The cross-section gives you a better idea. So we have the quaternary covering a very tertiary sequence where the Brussels formation is here, the late formation is here, and the event pop-up on that specific hill. Below the tertiary, you have the Cretaceous. That is also partly a very nice aquifer in the north part of Brussels, and the Paleozoic basement, where most of the geothermal exploration in Brussels are going on directly there. We are almost between 50 meter and 100 meter deep. To look for the problem, in September 2023, a company was asked to do a campaign, a geophysical campaign, or at least a geotechnical campaign. You have here a portable cone penetration test. It's a dynamic one with variable energy. It's a Panda 3 soil solution, a French company. The depth reached is 5 to 6 meter, and the idea is to look around the ground collapse. What are the elements or stability of the soil? The number 3 give very directly an information that there is again another cavity down there between 2.2 and almost 3.5 or 3.6 meter. So it's a bit more complex than simply the hole. The hole is not that large, but I try to make with a LiDAR a 3D model of it, but you cannot go inside, so it's a bit difficult. But there is a big slope going down to 2.5 meter, and then you don't see anything else. What is the background of this problem? The background is the exploitation of the lead stones. Lead stones are whitish. Limestones rich in silicium. These are Eocene, or for those that knows a little bit the French or France, you have the Lutetian age, the very famous rocks in the Paris Basin, but we have exactly the same age. The lead stone was exploited in a very large area around Brussels, also going towards the west and northwest in Flanders. And the name of that stone is also called Balogen. It was exploited since the Middle Age. So we have information since the 15th century. But in Brussels, it's a bit older because in those areas, you have open cast, more or less, so open quarries. In Brussels, there are no open quarries. These are underground quarries with, let's say, a range of depth between 15 and 25 meter depth. The most interesting 1 meter thick geological layers are the one that you can find in Brussels. So they have been strongly exploited, and the only document that is produced by a cameraman in 1955 and 1957 is that map. That map is only a kind of a summary of the presence of the lead formation, and the hatchet line indicate the potential area where those underground quarries should be present. Although we do not have any information nowhere. This is exactly the place where the house of the owner is lying. In this very old document, we have the knowledge of the presence of 2 underground quarries in 2 different streets. And on top of this, there are not only 1 gallery, but a group of galleries, but we don't know how much. We don't know their length, height, space. we don't know nothing. They are too old and there are no documents preserved at all. And on top, to complicate a little bit the information and the processes, the green line here is a tunnel that was constructed in 1925 that was sitting exactly at the same level of the underground quarry and met or encountered the quarries and the galleries during the construction. So the tunnel was stopped, and there are almost no explanation, no plan at all, because the train company today mentioned the fact they have lost the documentation and the information during the Second World War. So at least we know something, but we do not know too much. No ideas, as I told you, about anything of this gallery, except that they might be 100 meters long, and the second information that we took from the train and the engineers working at the time is explaining that some of the galleries were already affected by roof collapse. So, a second campaign has started with me 1 week ago with the same equipment, because the problem is it's a garden inside of a very densely populated area, full of buildings everywhere, no connection with the street directly, so it's very difficult to bring different type of technical equipment. So we decided to go for a very dense CPT exploration around the hole, essentially, and to confirm several suggestions or ideas in that area. On the left, this is a very typical results of a cone penetration test dealing with waste filling materials on top of 1.5 meter almost, then a quaternary sequence essentially affected by fluvial sediment on top, and going down to 5 meter with, let's say, loamy clay sediment, before entering at 5 meter to the tertiary clay of the Maldegem formation. And you can see that it is quite normal. You can follow, trace the results of the cone penetration test very easily. Although, if you look to that one, the sequence look very similar at the beginning, and then you have this issue. The values are totally different. They are much lower, indicating probably a void, a small cavity, and then the filling of the cavity by the collapse. And if you go a bit deeper, you can see that the results, it's very unusual. And probably is the filling with very heterogeneous material inside the root of the collapse of the structure, going downward, normally to the gallery exploited in the underground. So if we sum up with this kind of picture, you can see it's a very local case study. But you will understand that it is not so local for the future. But it's a very local case study where we end up with this idea that this is the hole. We have a collapse very clearly here. All those cone penetration tests indicate a cavity between 2 and 4 meters. The yellow one indicates an unusual response. Much deeper, below between 5 and 6 meters. And of course, some are perfectly stable, indicating no substantial issues. And so you can imagine 2 different areas. And another one very strange here, also between 5 and 6 meters. We do not have finished the geotechnical campaign because the owner of the house on the left, for you, has a terrace in the garden that is fractured and also cracking, falling down. So we decided to go for the similar exploration with compilation and test on that area. And the owner, the second house there, has also some issues where the walls are fractured also. So the problem seems to be larger than only one house. And if you want to understand a little bit what can pop up, is the only explanation that we found in literature, again by a cameraman, at a site that is the university campus of the Free University of Brussels, where I'm also teaching there, and where they have to construct the polytechnical building, so the foundation of the building. They met this kind of very strange structure. These are the root of roof collapse moving upward up to the base of the foundations, and also they found shaft. The idea, and we note from a very old drawing that in Brussels they use shaft at a very, let's say, close distance to reach the depth where they can exploit the laid stone. So the depth is here. You have probably galleries of 5 to 6 meters in height, where the laid stone was exploited. And then you have all these roof collapse moving upward, sometimes with an empty cavity, so they are void, sometimes not. And this is exactly what I'm suspecting in the garden. We have one example here, that is the hole with the ground collapse. And at the end of the garden, we might have something like that. So it means probably that we do not have one single gallery below the garden, but probably two. If I'm looking to the geological archive that we have in our survey, I found here a description of a collapse that has affected a house in 1910, and then two rough collapse in the street in 1926. And they were associated to the underground exploitations also. So if that one is the one of the owner that I'm presenting, if you trace this yellow line, it's 100 meters. This is more or less the length of the kind of gallery that you might expect in Brussels. And this circumference, this cycle, is related to the surroundings where we might have other galleries present, because the second group of galleries is associated to that street. The first one is associated to that one, but we don't know them, we never saw them, so it's probably a kind of a little problem for the future. And to sum up, this map has been produced by myself and my team to make a summary of the new geological layer formation mapping and cartography that we have done to cover the Brussels area. The brownish color corresponds to places where we are really sure that underground exploitation are present, and it doesn't affect one municipality, one district. So in that case specifically, the Geological Survey of Belgium is trying to help citizens because of the political complexity of our very small country. 20 years ago, the administrative competences regarding the subsurface has been regionalized. So Flanders and Wallonia took this into account because they were aware of mines and underground galleries. In the Brussels region, that competence has been forgotten and no one deals with it today. So if you start to discuss, and I was at the president municipality, no, the president of the regional municipality of Brussels to explain the case study, and they say, no, this is not our problem. Okay, but who is taking this into account? Go to the municipality or the smaller district. You discuss with them. No, it's not my fault. It's not my problem. We are not aware. So at the end, the citizen is alone. So it's why the Geological Survey took the idea of following it up and phase after those different geotechnical campaigns is to estimate the real importance of this ground collapse, to estimate the volumes, and have an idea of the second phase that the citizen has to discuss with his insurance. That is the stabilization. So filling with some materials, glue this material to fix the soil and to avoid any future problems in the future. So the story is not ended, but we now have a better idea of what's going on. Thank you so much.
Thank you, Javier, for a great presentation. This presentation about geohazard showed us clearly that besides sophisticated data systems and GIS and BIM techniques, still in some cases individual approach by expert, skilled and passionate for site investigation is essential to find a solution for problem. Now we will have another online presentation. It will be a presentation by our colleague Philippe Verens from Swiss Geological Survey from Switzerland. It will be about a BIM, a building information model of Mount Terry underground research laboratory. Philippe, can you hear us?
You hear me?
Yes, so we
Very
give
good.
you the floor. We have downloaded 2 movies from your transfer. So they are on a stick, so I pass them to our colleague from IT. So if you need to refer to them, please tell us.
Fine.
So we will put them. Okay.
It's a little bonus. So today I will present a BIM Monterey project. This is not my work, it's work of a colleague, Stefan Volken, who is responsible for this project, but he unfortunately couldn't be there, so I will present it. First, the Monterey Rock Laboratory is a rock laboratory that's located in the Swiss Val Jura Mountains. What you see in this image here is the Jura Mountains with a road tunnel and an extra safety tunnel next to it, and right in the middle there at the red square is the rock laboratory, which you see bigger in the right top corner. Within this rock laboratory, there's a large project. It's an international research project that has been going on for 28 years, where the main topic is to study the Opolinus clay, which is the only proposed host rock for high-level radioactive waste in Switzerland. Within this project, there are many international partners from 10 different countries. So it's really a long ongoing research laboratory. As I mentioned before, the tunnel is located along a motorway tunnel and the security gallery of that. And it was the first construction took place in 1996, where the first niches were built. And then with each ongoing time period, the laboratory was slowly expanded, as you can see from this image. That is also the reason that at the moment, or at the last couple of years, it was decided to transform this the information of the rock laboratory, of the tunnel system, into the BIM system, because at the moment all the information was lying there as CAD format files or PDFs or Excel files. So it's become too big to manage in such a way. SwissTopo, or the Geological Survey in this case, has certain tasks at this rock laboratory. So we are responsible for the management of the international Monterey project. That is the project with the 10 different nationality partners. We're also responsible for the operation of the rock laboratory, as well as the underground safety, but also for the planning and conducting of experiments, either our own experiments or supporting the experiments of the partners. And lastly, which I think is very important, is communication, and not only to other authorities or research institutes or industry, but also to the general population. So we have a visitor center where people can actually visit this rock laboratory and get a tour. And that's a very good way to inform the people on the research that has been going on there. In order to implement this BIM method into this tunnel system, a couple of use cases were defined. So most importantly, it was the interaction between the geology and the laboratory infrastructure. That was the start of this whole project, because we are at the Swiss Geological Survey, first of all, geologists. But as it turned out, it encompassed much more than just that. So secondly, we needed to make an inventory of the laboratory infrastructure, as well as all the geological objects. So this is a retro BIM. This is making an acquisition of all the existing infrastructures. Not like when you build a new tunnel and you start with a BIM. This is like refitting a BIM to an existing tunnel system. Then also one important factor would be the development of an interface to share the data, for which IFC was chosen as a format. So we can exchange the information from our system to, for example, different projects, or in case of laboratory expansion, to the people building the expansion. Then also operation and maintenance, because the tunnel has lots of technical infrastructure that needs maintenance, which the condition needs to be checked and damage needs to be assessed, and that can all be maintained in such a BIM system. As I mentioned, new experiments and drilling planning needs to be done within this system, and at the moment there are 1,300 boreholes or something within this tunnel system. So it's also a matter of having everything in 3D space, so you can actually see where your existing boreholes are, and decide where you want to plan new ones. Then we also thought of the BIM infrastructure as being a basis for simulations, for example, fire hazard simulations. And in the end, which is also part of the general BIM method, is the end of the life cycle of a building. So in this case, if the research project would be finished and the laboratory would be dismantled, then this would also be a very useful tool in that regard. And then finally, public relations. So the visitor tours can then be an additional feature, like VR or AR can be used in visitor tours. So people would actually see the geology and the experiments in an augmented way when they visit the laboratory in real life. But before we can start this work, we needed to think of the definition of the information that would be incorporated in such a system. And this is probably the most important part, is the structure of the object catalog. So in order to fill this catalog, the existing infrastructure in the laboratory was inspected. That means all the CAD plans and the PDF plans, the Excel list, everything was collected. It's a very heterogeneous data set. Then the currently existing applications that were being used in the rock laboratory were assessed and also viewed what kind of data was in there. So there's a borehole information system called BIS. Then we use Move for 3D modeling of geological features, and Fulcrum is a software where you can acquire measurement data in the field. So all this information was also gathered. Then a tedious work of making a photo documentation of all these existing assets, so making photos of doorknobs and light switches, everything in the laboratory. And then finally defining categories for those assets and asset types. That resulted in these categories, as you see here. So they're very basic categories, and then an extensive list of asset types. And there, for geologists, there are two, I think, important features. One is at the bottom right corner, you see that we have a little greenish box where we have boreholes, vaults, geological units, and contacts. And boreholes actually, so these are the real geological features. And then we also have boreholes occurring here in the asset type of the infrastructure. because boreholes also build a piece of infrastructure, so that's why they occur twice in this list. Then for the collection of data, the whole rock laboratory was scanned again with a laser scan technology. We used more than 400 stations, and more than 40 billion points were generated, which were then, with the scan to BIM method, the assets were extracted from that, and a new clean tunnel mesh was generated. Approximately 4,000 objects could be extracted and then categorized and typed according to the structure I mentioned before, and all the attributes were attributed. And in terms of linear objects, there were lots of linear objects with an approximate length of about 5 kilometers. Also, the geology was taken from the MOVE environment and put into a BIM suitable environment, which you see here. So this is the geology encompassing the tunnel. The tunnel would be inside of this box. You see here the different units. And if we visualize the tunnel, then we see here the contact in this transparent, with the transparent colors. And we see at the location of the tunnel, the intersection with different fault planes and different categorized in different colors to their respective shear sensors or orientations. And we also see the boreholes now much clearer. So you see how busy it is down there and how difficult it is to plan a new borehole. And the boreholes are here part of the geological asset type set, because the geological information in the borehole is displayed. Then in order to, so if we've collected everything, all this information is available and made available for a BIM in a BIM setting. Now the question is, how do we manage all this data and how do we deal with that? So there we thought of building an application which should be a cloud-based web solution, where various roles could be defined depending on who's the operator of this application. The solution should be as open as possible, meaning that we opted for IFC 4.3. The data storage should also be generic, so no common data environment where the access is proprietary, but something very generic. Also, a requirement was that it would be possible to generate 3D scenes, which means a 3D scene is basically taking the information from that database to your requirements. So whatever you want to see, you can extract from the database environment, visualize in a 3D viewer, but also the possibility to export that information, that 3D scene, into IFC. Furthermore, the people who work at the Rock Laboratory were very much insistent on having a high performance point cloud integration into the 3D viewer. And the whole system should be flexibly to expand. So this is an overview of what it looks like. In the center, there's the BIM Monterey web app. From there, you can manage all the assets we've talked about before. Also here, there's the storage of the 3D objects of geology and infrastructure, and the scenes can be generated using parametric modeling. So that means that the actual geometry of the object is not necessarily stored in the database. It's geometry is defined over its attributes and can be generated on visualization from those parameters, hence parametric modeling. Yes, and then also there's an export on the right side of the image. There's an export to IFC, which means that you can select your data as you wish in the 3D viewer, in a 3D scene, and you can export that to cooperate with third parties. I will not go into much detail on that, but there are some benefits to not storing the geometry directly, but using parametric modeling. That proved to be very useful. And I just want to show another overview of the application. So this is the asset management system, where you can select assets based and filter them based on the category, the asset type, but also on the tunnel section, so the gallery number. For example, in this image you see gallery 18, and then the meters along the tunnel axis from 93 to 271, for example. And on the left side of the image, in the dark gray overlay, you see that we are in the assets drop down, but you can also go to 3D scenes or view the whole catalog, and you can see which users and organizations have access to particular things. Then there's also the 3D scenes, as I mentioned before. So this is an extract then from that data set, from which you can then open that in a 3D viewer or download everything to IFC and share with third-party members. And I think the lessons learned is that this well-structured object catalog, which I showed at the start, is a must, and it's very time-consuming, and it takes a lot of thinking about what you want to incorporate in such a system. What is the extent to what you want to do this? And the parametric modeling of not storing the geometries explicitly, but more implicitly, that offers a lot of flexibility. Then having a generic data storage also is beneficial, not only for it being more open, easy to use, but also for the possibilities of parametric modeling. And then, since this new laser scan of the whole lab, that was a very big exercise, and it turned out that it was very helpful to have a very competent contact person on the contractor side, and that was really important to get this project to work. So that's also a hint for if anybody's interested in doing something similar. And then IFC, finally, the IFC format is a suitable exchange format, although it's not very widely supported yet. And maybe I should mention the timing of this whole thing. So it started, the pre-study started in 2022, and then the actual work on the object catalog started in 2023. And at the moment, everything is being finished. So at the end of the year, the test phase is over, and from 2025 onwards, this will be operational. Okay, that's it. If you have any questions, don't hesitate to take note of the contact details of Stefan Volken at the bottom. He's happy to have contact about this topic. Thank you.
Thank you, Philip, for your presentation. Unfortunately, due to the lack of time, we won't be able to present the movies you sent us, but we have the movies presenting the virtual tours of this BIM Monterrey lab. So later we will show them for interested people at the booth in our expo zone. And this presentation showed us how the 3D innovative solutions are essential to communicate geological composition for general public and can be used for social acceptance for projects such as underground nuclear waste storage. And it shows us also that complexity and interoperability of data, it's going more and more IT topics into geoscience. So it seems that it's inevitable and we have to deal with this. Okay, so the last presentation will be from our partner from Guideline Geo. It will be, the speaker will be Harry Hicks from Guideline Geo company, and it will be about geophysical tools used for engineering, geology, and geotechnics. Harry, the floor is yours.
Hello. Yeah, my name's Harry Higgs. I'm an application engineer at a company called Guideline Geo. We are an equipment manufacturer of geophysical instrumentation. And I'm going to present geophysics, an efficient tool for prediction, prevention, assessment, and remediation in engineering. So first, I'd just like to talk about efficiency in engineering and how geophysics can be a cost-effective method for providing engineering data. So in the first figure A on the left, we have a situation which represents a 2D planning environment where we have 10 equally spaced boreholes sampling the bedrock. If we move to a 3D planning scenario, maintaining the same data sampling, we would require 100 boreholes. And an alternative approach would be to substitute boreholes for the inclusion of geophysics.
Okay, Harry,
maintaining.
Excuse me, there is a request from the translators that you could put the microphone closer to your mouth. Thank you.
Okay. So we substitute boreholes for the geophysics, which then samples the bedrock in between boreholes. So figure D just shows a comparison between figures B and C. The orange line showing purely the number of boreholes required for a given area without geophysics, and then maintaining the same data sampling, but with the inclusion of geophysics, So this is just showing the efficiency that can be gained from including geophysics with geotechnical investigations. Another way to think about the efficiency that geophysics can bring is in probability. So if we're looking for a, say, 1 by 1 meter squared buried target, such as a buried mine shaft, and our accuracy of the historical maps is low, so we know the position within 100 by 100 meters, then to use purely point source geotechnical intrusives to find that mine shaft, we would have to plan for up to 1,000 intrusives within that area to have a 100% probability of finding that mine shaft. And the alternative would be geophysics, where we can scan the entire area in a very short period and then target geophysical anomalies that are indicative of the feature that we're looking for. So as an example of this, cable route case study in which GPR is used to assess bedrock depths through some overlying peat deposits, and using the GPR derived data as a priori data, which informs the drilling. And by doing this, we can reduce the project's cost. So in the bottom left satellite image, we have the fictitious drilling program that would be required with no additional information. So the drilling positions are a constant interval to obtain the necessary coverage across the pipeline route. On the bottom right is the actual drilling used with the presence of GPR data. So the intrusives are planned around the deeper peat deposits. And then the table at the top shows the comparison between a program without the GPR and a program with the GPR, and the amount of intrusive soil sampling reduction that was achieved with the GPR, which averages 50% across the 3 test methods used. And geophysics can also be used for de-risking, so identifying subsurface conditions that may pose a risk during construction or development. By providing a continuous data coverage, it can be used as a tool for quantifying risk. I know we're a little short of time, so I'm going to leave this figure and jump into an example of this, which is a project I worked on in industry for high-speed rail, where we are assessing the ground for the risk posed by critical velocity effects, which is a phenomenon that occurs when trains approach the velocity of the surface rayleigh waves in the ground. And this effect has affected high-speed rail routes in Europe before, and which have resulted in costly remediation measures and delays. So this paper by Holm et al. Illustrates this well. This is a site in Sweden near Gothenburg, where in 1997 the existing rail line was introduced to high-speed trains. And they found that the rail displacement with high-speed rail was excessive. So in the figure 1 on the top right, the top solid line this is the upwards deflection of the rail, and this bottom line is the downwards deflection of the rail in millimeters, and the horizontal axis is the train speed. So at 200 kilometers an hour, which relates to about 55 meters per second, the total deflection in the rails is about 15 millimeters, which is intolerable, and as a result, the trains needed to be cut by their velocity cut by 50%. To bring them down whilst remediation was taken. The image in the bottom right shows the shear wave velocity profile for that same working area. And the shear wave velocity is very closely related to the Rayleigh wave speed. So we see that we have 60 meters per second at the surface, reducing to about 35 meters per second at just 2 meters depth. So this illustrates the interplay when we have very low velocity ground speeds, and then we have trains that are operating close to those ground speeds, resulting in these excessive displacements of the rails. So this is what we want to avoid. And we want to use geophysics as a way to assess the risk from these types of effect. And that can be done in a very robust way using MASW, which is an acronym for the multi-channel analysis of surface waves. And using this method, the data can be collected very quickly, especially using seismic land streamers, perhaps up to a kilometer per day, depending on the data density. And we can use simple cost-effective sources such as a sledgehammer or a Betsy gun for depths of up to and greater than 30 meters, which is ideally suited for this application. This is a seismic land streamer. So it's a belt, orange belt with vertical geophones placed at constant intervals. And if this plays, this is the data collection on site. So we're trialing a Betsy gun there. And you can see the data being recorded in real time and then displayed on the seismograph. So we acquired data along 3 parallel lines with a total width of 150 meters running along the proposed route of the new track. The survey area is underlain with clays and weak underlying mudstones, so they're considered an at-risk area for critical velocity. We trialed both hammer and Betsy gun. We used 48 channel arrays with 1 meter spaced 4.5 Hertz vertical geophones, and we moved the seismic array forwards in increments of 4 meters in between tests. Just a note on what we're looking for, which is Rayleigh waves, which are the slowest moving seismic wave. They attenuate quite quickly and they occur at the surface of the Earth, but they also are the slowest moving with the highest amplitude. And one particular element of surface waves is that they're dispersive, which means with different frequencies travel at different depths. So the lower frequencies travel at greater depth at the velocity of the materials through which they travel, and the higher frequencies travel closer to the surface. So we can make use of that to derive continuous velocity profiles from the data. And this type of data is best observed in the frequency domain. So what we do is we take our time domain data from our seismograph, which is shown on the leftmost image. We run a 2-dimensional Fourier transform to obtain a velocity frequency spectrum, and in which case here the colors represent the energy, where red is highest energy. So this is plotting the shape of the Rayleigh wave dispersion at the site. We can then analyze those bulk values, apparent Rayleigh wave velocities, or run them through 1D inversions to obtain depths to and thicknesses of discrete layers. And if we want to, we can then grid those as 2D velocity profiles, which is the image you see on the right-hand side. So this is an excerpt of the results from the study. We have a profile distance in meters along the horizontal axis and elevation in meters on the vertical axis. And then here the colors represent velocity of the materials present. So the blues are the slowest velocities at about 160 meters per second, rising towards 700 meters per second with the reds. Then I've drawn on the design level of the track bed. And as you can see, it's now very easy to assess the velocities present for the risk to the infrastructure of these critical velocity effects. In this particular case, the design speed is 360 kilometers an hour, which relates to approximately 100 meters per second. And I'd like to just talk, if I have time, about a second case study, because it involves both geotechnical investigation and geophysical investigations working together to provide information. So this is an urban setting, and we're evaluating a large pile that was originally constructed in the 1950s on a railway flyover in Birmingham in England. The plans were uncertain, to say the least. They're just hand-drawn. So the aim of the survey here was to determine the depth of the pile, and also confirm the presence of an underream, which is the expanding of the pile at the base here. So to do this, we sunk 2 boreholes, one on either side of the pile. That's shown in figure 2 with the 2 blue expressions of the boreholes at the surface. We used parallel seismic to determine the length of the pile, and we used cross-hole seismic to evaluate the presence of the underream. So just looking at the parallel seismic, we're making use of the travel times of the P pressure waves through the pile and the surrounding material. And we plot the first arrivals against depth. So figure 3 shows the generalized layout. We hit the top of the pile, and then we time the wave to reach the receiver, which is located in the adjacent borehole. When we're analyzing this data, we can plot figure 4. So we have delay time on the x-axis and then depth in the borehole on the y-axis. And then we're plotting our data, and we're picking the first arrivals. And then we are interpreting changes in slope for the material properties that are in the borehole. So we have 3 changes. The first near the surface, denoted with the blue, is the direct wave as the wave travels just through the surrounding materials. Then we have the refracted wave, which actually had a velocity consistent with the steel rebar within the pile. And then we have the third green area, which is the velocity of the materials beneath the pile. So we want to find the toe of the pile here, and that relates to the second change in slope here at 11.5 meters, plus or minus 2.5 meters. And then the cross-hole seismic, that just makes use of the travel times through the pile and the surrounding material. But this time we have a receiver in one borehole and a seismic source in the opposing borehole. And we lower both down at constant elevation changes, so they're always on the same elevation, and just measure the travel time between boreholes. So the results for this section here, again, this is plotting data in a similar way, so delay time on the x-axis, depth on the y-axis, and I've highlighted in color the 3 different changes we have. So we have blue here, which we interpret as representing an initial widening of the pile near to the surface. Then we have constant travel times, and because we know the velocity of the materials around the pile and the velocity of the pile itself, we know that the ratio between the 2 materials is the same. So we're actually looking at just a vertical constant diameter pile between the depth ranges of 6.5 and 8.5 meters below ground level. And then most interestingly, this green area here, where we see a constant delay, reduction in travel times. And this is due to the presence of the underream. As the pile becomes wider towards the base, the faster velocity concrete means that the ray path has a shorter travel time. So we can actually see that the underream begins at about 8.5 meters below ground level and continues all the way to the base. The cross-hole seismic also, after 11.5 meters, shows later travel times again. So we know we've gone past the toe of the pile, and that's nice to have an independent verification on the pile depth, both agreeing at 11.5 meters. So we were able to show the presence of the underream and also compare against the as-built, and the as-built put the pile at a depth of 9.5 meters. So it's good to have some confirmation. We were also able to quantify the additional amount of concrete that the wave would have had to travel through by knowing the velocities of the materials present. So in the underream, we're just plotting in this table the additional amount of concrete that the wave has traveled through. By just doing some forwards modeling of the wave, so figuring out the shortest travel time that the ray path would have had to have taken, we can then actually provide an estimate of the underream diameter at the base by having but requiring the initial diameter above the underream, which was supplied by the client. So then we have a value plus or minus some error, which is just the propagation of the errors in the experiment plus the uncertainty in the client's own measurements. Very almost finished. So just to finish off with, we mentioned the necessity for 3D planning and becoming more of a requirement as we see it. So that's particularly helpful when you have hardware that's designed for 3D data collection, and particularly useful in utility surveys as these kind of 3D GPR systems, because they provide a very high level of data density. So this last case study is just around a warehouse where they want to expand the warehouse out to the side. So they need to put in some geotechnical drilling. So this is just data acquired using an array system, which took 30 minutes to collect 800 square meters. And the lines here, linear features, relate to the utilities. And then that was just processed up very quickly. And these red dots denote the drilling positions, which can quickly be interpreted from the data. So that's another way of reducing risk in our ground models. So that brings me to the end of the presentation. Thank you for listening. Just have to acknowledge Socotech UK Limited for allowing me to talk about some of my projects whilst I was working with them. And just to note, there's also an opportunity to use the Mala Mirror compact GPR system, which was used and provided the data for the previous case study outside. And the geophysical equipment used in the production of the case studies are available for our distributor in Poland, GeoRadar. These are the citations used in the presentation. And yeah, thank you for listening, everyone.
Thank you, Harry. Ja tak na szybciutko, bo mamy 30 sekund z tego co wiem. Zapraszam na 17:30 na taki krótki pokaz Miry 3D. To był ten radar, który widzieliście Państwo na samym końcu. A jestem Anna Grofik i jestem właśnie przedstawicielem firmy Georadar. Jesteśmy dystrybutorem w Polsce sprzętów Guideline Geo. Dzięki.
Thank you. Yes. So thank you, dear guests, for your endurance. We lasted till end of the third session, so our workshop is almost finished.